Good afternoon, everyone. My name is Hang Kim from Chosun University, South Korea. The topic of my presentation is the effect of stress strain and load ratio on the Ratchet deformation of nuclear structure materials. This is outline of my presentation. First, background. Systems, structures, and components of nuclear power plants are designed to have sufficient safety margin under design basis earthquake conditions. When the earthquake exceeds the design basis, the large amplitude cyclic loads occur regionally in vulnerable areas. At this time, the deformation of and failure behavior could be different from that considered in DVE. So for reliable structural integrity evaluation, it is important to understand the deformation and failure behavior of the vulnerable parts under large amplitude cyclic loads. In this regard, previous studies have been conducted, and most studies conducted displacement controls, and load ratio is -1. But seismic load is generally a combination of displacement and load control cyclic loads. Also, the stress strain is not uniform, and there are areas where stress and strain are concentrated. So it is necessary to consider the stress strain and strain concentration under the large amplitude load control cyclic loads. Therefore, the objective of this study is to identify the effect of stress strain and load ratio on deformation and failure behavior under the large amplitude load control cyclic loads. Based on these studies, based on these objectives, the cyclic tests were performed under the large amplitude load control cyclic loads. The response load displacement curves, cyclic deformation behavior, and failure cycles were analyzed from the test result. Finally, the effect of the stress strain and load ratio on the deformation and failure behavior of nuclear structural materials was identified. And materials, SA5 grade 1 roller steel and SA312 TP316 stainless steel piping materials used for structural material in nuclear power plants used for cyclic test. And the specimen, the roundabout type specimen with notch ready of 1.5 millimeters and 6 millimeters. And for all tests performed at room temperature, regardless of materials and notch radius, and at the load ratio of -1 and -0.5 for 75% maximum load, and at load ratio of -1, -0.5, and 0, and remaining load conditions. Here, monotonic loads, maximum monotonic loads, P monotonic means maximum load of each specimen tested under monotonic conditions. The test machine for used subhydraulic universal testing machine with 100 kilonewton load cell, and the dynamic extensometer with gauge lengths of 12.5 millimeters were measured displacement. And the test speed was quasi-static rate, and the data acquisition, we collected 200 data per cycle, and all tests were performed until the specimen fractured. In order to obtain the P monotonic for the notch specimen of each materials before performing the cyclic test, the test was performed under monotonic loads, and the test results are shown. And the normalized the normalized displacement is the length measured out of the notch section and normalized to the gauge length. The result shows that regardless of the material, as the notch radius decreased, the maximum load increased, and the displacement to maximum load and displacement to final failure decrease. From now on, these are the results of the cyclic test. In roller steel, for all test conditions, regardless of the notch radius and road ratio, the hysteresis roofs are ships, and the area of the roof gradually increases. This indicates that the ratcheting phenomena occur in all test conditions. In stainless steel, as the like in roller steel, for all test conditions, the hysteresis roofs are shifts, and the area of the roof gradually increases as the road constant amplitude is repeated, regardless of the notch radius and road ratio. This also indicates that ratcheting phenomenon has occurred in all test conditions. And to examine the deformation behavior of each materials, and the mean of the maximum and minimum normalized displacements for each cycles in the hysteresis loops shown earlier for the examine. From the graph, for the roller steel, the larger compressive load, the larger rate of increase in mean normalized displacement regardless of maximum load and notch radius. In other words, the smaller road ratio and the faster ratcheting rate. Generally, the smaller road ratio, the larger road amplitude, and the smaller mean stress. According to the previous studies, it is known that as the amplitude increase and the mean stress increase, the more severe in ratcheting rate occurs. The result of the roller steels shows that as the road ratio decreases, the ratcheting rate becomes more severe, which means that the effect of the increasing road amplitude was greater than the effect of the decreasing mean stress. In the case of stainless steel, unlike roller steel, the trend was different. For regardless of the maximum load and notch radius, the smaller compressive load, the larger rate of increase in mean normalized displacement regardless of maximum load and notch radius, except maximum load of 85% or less, and load ratio is 0. In other words, the larger load ratio, the faster ratcheting rate, except these conditions, and the result of the stainless steel shows that the effect of shows that the road ratio decrease, the ratcheting rate became slower, which means that the effect of the increasing mean stress was greater than the effect of decreasing stress amplitude. However, the normalized displacement is not representative not the representative of the strain in the notch section. So we performed the final element analysis to find the average of the equivalent plastic strain in notch cross sections and define the plastic strain and convergent. We converted to plastic strain to see the behavior of the function of the notch radius, as shown in figure. Regardless of the materials, the ratcheting rate is faster for notch radius of the notch radius and 6 millimeters at road ratio of -1. However, when the road ratio goes to -0.5, both materials show similar ratcheting rates as function of notch radius, and at a road ratio is 0, the ratcheting rate is faster for notch radius of 1.5 millimeters. The difference in ratcheting rate with notch radius of each road ratio is thought that to be due to the difference in deformation in initial cycle. Examining the maximum normalized displacement of initial cycles as the function of notch radius normalized by monotonic displacement shows that initial deformation is larger at faster and ratcheting rate. To understand the difference between the materials, the mean plastic strain for each cycle was compared by materials. As shown in the figures, roller steel shows faster ratcheting rates than stainless steel, regardless of the notch radius and rod ratio. This difference is due to the cyclic hardening characteristic of the materials, which is known to cause less ratcheting is in materials that exhibit cyclic hardening compared to the materials that do not. And the failure cycle is shown as the function of rod ratio. For lower steel, the larger compressive rod, the lower failure cycle. However, for stainless steel, there was a slight difference from roller steel. And for maximum load was under 85% or less, and the rod 85%. The failure cycle decreased with increasing compressive load. On the other hand, at 99.8%, the failure cycle increased as the compressive load increased. Generally, the increase in failure cycle as the compressive load decrease is constant with the increase in life as the amplitude of the cycle loads applied to specimen decreased, except for the 99.8% of the stainless steel. However, when the maximum load of stainless steel is subjected to very large cycle loads, the increase in the failure cycles due to increase in compressive load is judged to be related to large cyclic hardening effects of stainless steel. In other words, in the case of stainless steel, the load-bearing capacity of the specimen is improved due to cyclic hardening caused by the increase in compressive load. And final conclusion, first, SA5 grade 1A roller steel shows more severe ratcheting rate as the rod ratio decreased, regardless of the notch radius. However, SA312 TP6 or 316 stainless steel shows more severe ratcheting rate as the rod ratio increased, regardless of the notch radius, except for some rod conditions. Regardless of the materials, regardless of materials, ratcheting rate was more severe for large notch radius at the rod ratio of -1. However, at the rod ratio of -0.5, ratcheting rate was similar regardless of notch radius. And at the rod ratio of 0, ratcheting rate was more severe for smaller notch radius. Third, regardless of the notch radius and rod ratio, SA5 grade 1A roller steel shows more severe ratcheting rate than SA312 TP316 stainless steel due to the cyclic hardening characteristic of each materials. Final, for both materials, the failure cycle increased with increasing rod ratio in most cases, regardless of the notch radius. However, for SA312 TP316 stainless steel, the failure cycle increased as the rod ratio decreased in the case of the maximum load of 99%, 99.8% regardless of the notch radius. Thank you for your attention.